I'm sharing my screen. Yeah, a very good evening to all of you. My name is I am Sanat Kumar. Okay, I'm working as a trainer in Gnanodaya VLSI. So welcome to this session on VLSI. So whatever the job opportunities in VLSI semiconductor industry, what are the job opportunities we'll see. Okay. Before that, we'll see what is this VLSI. Okay. So VLSI is nothing but very large scale integration. Okay. So VLSI is nothing but very large scale integration. That means you already know that is millions of transistors we are fabricating on a, single IC. So that means if you see like so many applications are there. So like you have like your one second, please, please. చెప్పండి మేడం. హలో, హలో, హలో.
హలో
చెప్పండి మేడం.
సార్ వీళ్ళకి క్లాసెస్ కంప్లీట్ అయిపోయిందా అంటున్నాను.
అయిపోయింది మేడం, అయిపోయింది.
అవునా?
హ్మ్.
బట్ వీళ్ళు టికిల్ అని సంథింగ్ టాపిక్ అంటారు, అది అవ్వలేదు మ్యామ్, ఎవరు చెప్తారు అని అడుగుతున్నారు.
మ్మ్. ఓకే, ఓకే. మ్మ్, మ్మ్.
సో నేను అది హార్ట్ మెన్షన్ చేశాను సురేష్ సార్కి.
ఆ,
సో ఇన్ కేస్ వాళ్ళకి మీ దగ్గర నుంచే కావాలి అని అమ్మాయి పర్టికులర్ శివాని అయితే మీకు డిస్కస్
ఓకే.
శరత్ సార్కే కావాలి మాకు అని. సో
ఆ,
నేను సురేష్ సార్ కూడా చెప్పాను,
ఆ.
కావాలి అంటే సంస్థ దగ్గర ఇప్పించి వాళ్ళకి అని చెప్పారు.
సరే, సరే. ఇప్పుడు నేను ఒకటి ట్రైనింగ్లో ఉన్నాను. ఇది ఇప్పుడు ఒక క్లాస్లో ఉన్నాను. ఈ క్లాస్ తర్వాత షెడ్యూల్ చేద్దాం. మ్మ్.
ఆహా లేదు సార్, మీకు కావాలంటే నేను రేపే అదే మండే
రేపు
షెడ్యూల్
మండే
చేస్తాను
చేయండి,
మీకు.
మండే చేయండి, మండే చేయండి.
మండే చేస్తాను మీ ఇష్యూ, బట్
మ్మ్.
అది ఇన్ఫార్మ్ చేస్తున్నాను వాళ్ళకి ఆ టాపిక్ మీ గురించి మీ దగ్గర నుంచి కావాలి అని.
సరే, సరే. ఓకే, చెప్తాను మేడం,
ఆ,
చెప్తాను.
సరే సార్.
ఓకే. Yeah, okay. Sorry for the interruption. Okay. Yeah, so like VLSI is nothing but it's a very large scale integration. So basically, like millions of transistors we are fabricating within an IC. So, like if you consider mm, uh, previous, if you see whatever the electronic gadgets you are using, okay, inside so many ICs are there. One IC will do some multiple operations, okay, it will do some multiple operations, okay. And if you take one example like we consider your led tv, okay. Led tv, it will consume like led or smart tv, it will consume around 12 volts of a power supply. Suppose if you consider some previous olden tvs, okay, olden tvs that will take around 230 or 250 volts of power supply, okay. So here that means so what happening means day by day so many millions of transistors we are fabricated within an IC, and we are using using CMOS technology. CMOS technology is nothing but complementary metal oxide semiconductor technology. There it consists of having high package density and low power consumption, and also that Moore's law. So Moore is a scientist. Moore is a Intel founder. He given a statement that the transistor count doubles for every day, every 2 years. Okay, so that Moore's law is the statement is till now it's means proving. Now we are in which technology means like we are in 3 nanometer or 2 nanometer technology, and that is different distance between this what we call the distance between source and drain is nothing but length of the channel, okay. So the length of the channel is 2 nanometer or 3 nanometer. So that much technology we are working under. So many that means we can say that whatever the AI related and augmented reality and whatever the smart IoT, okay, whatever the technologies are coming, so that is interrelated with VLSI. Okay, VLSI is developing means these are depending on this VLSI. Suppose AI related is coming means we need to fabricate more powerful ICs. Okay, so all are interrelated. So basically, I want to say about what is the job market, and I want to say, so I will give some exposure on VLSI. Okay, so VLSI like front end and back end. So what will be there, and those things I want to discuss. Okay. Yes. So my voice is clear, no? Any? Yeah, yeah. So please give any response so that I will move forward. Yes or no, or shall I move forward? Anyone? Hello. Okay, thank you. Okay. So what are the job opportunities in VLSI semiconductor? We'll see. Okay. So basically, if you take like these are the contents I want to discuss. Okay. So first we'll see the VLSI semiconductor industry. So basically in the VLSI semiconductor industry, there are three companies are there. Okay. One is product-based company. Okay. One is product-based company, and next one is service-based company, and next one is EDA companies. So what are these product-based companies? Product-based companies are nothing but they will they will produce their own ICs. Okay, like if you consider the product-based companies, the product-based companies are if you consider. So I'll show you the product-based companies. These are the product-based companies like Samsung, Intel, TSMC, Micron, Qualcomm, Nvidia, Broadcom, MediaTek, TI, AMD, Infineon, Apple, okay, ST Microelectronics, and NXP. So these will produce their own ICs. Okay, so like total like 20 product-based companies are available in our all over the world. Okay, so these are the product-based companies. And service-based companies are nothing but they will not produce any IC. Just they will give the service to these product-based companies or EDA companies. Okay, like you already know, like Capgemini, Tisol, USD Global, Infosys, Samsung, okay, Mirafra, okay, Apex, okay. These are nothing but L&T and Wipro, okay, HCL. All these are nothing but we call as a service-based companies. So apart from this, you have around 1,000 plus service-based companies are there in Hyderabad, Bangalore, Noida, and all over the India. Okay, and what are EDA companies means? So EDA companies are nothing but EDA is nothing but electronic design automation. Okay. So electronic design automation means suppose like you have different types of technologies are there. No. So you have like SSI, okay, LSI, okay, small scale integration and medium scale integration and large scale integration, very large scale integration, ultra large scale integration, giant scale integration. So these are nothing but what different versions. So like if you go with the 1961 like that, so you have small scale integrations only. Small scale integration means you have only one transistor is there. Okay, and so that means if you design some 100 to 1,000 transistors are there, easily manually you can fabricate. Okay, but you have some some millions of transistors are like 100,000 crore transistors are there. Okay, so 1,000 crore transistors, so millions of transistors are available within an IC. So manually it's not possible. So we need some EDA tools, electronic design automation tools. Those are nothing but Cadence, Mentor Graphics, and Synopsys. These are nothing but they will provide the EDA tools. Okay, so in the VLSA front end, you have some EDA tools like suppose in the RTL design, you have some EDA tools for verification. You have some EDA tools for the synthesis or from the static timing analysis or for DFT. You have different EDA tools. So Synopsys will provide some Synopsys VCS tools are there. Cadence they will provide some Xcelium or for the verification they will provide Jasper. Okay, like that. And Mentor Graphics it will provide like Model Sim or Questa Sim. Okay, AMD also provides some tools that is Xilinx Vivado. Okay, in the back end also you have some tools like what we call for back end Cadence Innovas tools are there, and Synopsys tools are also available. So these are the tools. So what they will do? Like we need to guide these tools, okay? So that we are the VLSI engineers. We need to guide that tool so that during the designing process we need to guide that tool. The tool will work. Okay, tool will not work oppositely automatically. Okay, somebody unmuted. Please mute yourself so that Charan, just mute yourself. Hello, hello. Hello, mute yourself so that any questions, any queries, so that you can ask in the last. Okay, yeah. So these are nothing but like so we have EDA tools, product based, service based companies will always synchronize up. That means they will like we call like they will combinedly make the technology developable with the support of VLSI engineers, okay, with the support of what VLSI engineers. Okay, so this is the basic VLSI semiconductor companies. So basically before that I want to go into this basic physical flow. Okay, so this is the detailed flow ASIC. Okay, ASIC, so that means VLSI target devices are two. Okay, one is ASIC and next one is FPGA. ASIC is nothing but what? Application specific integrated circuit. Application specific integrated circuit means suppose whatever your household applications are that ICs that used only for particular application. Okay. Let us consider your mobile is there. Your mobile is ASIC and we call yeah, in the household application also your AC. Okay, your AC, your smart TV, and washing machine. Okay, so that means your suppose your AC, whatever the IC you are using in the AC, you can't use in your washing machine. No, so that is used only for the particular application. Okay, that is nothing but ASIC. Okay, in automobiles also, airbag system and auto lock braking system and engine control system. There are specific ICs which will take care of that particular application. Okay, so that is nothing but ASIC. Okay, that is nothing but ASIC. Suppose you have a 3G mobile. Suppose first you have switch type mobiles and related to the communication you have 2G, 3G, 4G, 5. Now we are working on 5G. Okay, suppose if you have a 3G mobile, you can't use for that same mobile with a 5G mobile. Okay, why? Because that is a ASIC that is only designed for particular application. Okay, so that means once the program is done, so we can't change. That is nothing but ASIC. Okay, FPGA is nothing but programmable. Programmable means what? We can configurable. So we can do program. Suppose if you want to design some FSM, okay, so you can write the program and you can port it into this FPGA so that your FPGA will work based on this FSM. Suppose after some time, if you want to design some counter, okay, again you can erase and you can port this into this FPGA so that your counter will work. Okay, so that is the main VLSI target devices. Those are FPGA, so ASIC and FPGA. Okay, so this is nothing but ASIC application specific integrated circuit flow. Okay, so each and every level have different engineers are there. Okay, so design specification is nothing but suppose so this is nothing but we call as a design flow. So design flow is nothing but so we call this is a process of design or market requirements till the outcome of fabrication. That means based on the market requirement I will make my IC. Suppose if you are designing for IC for some computer related application, so that is you need to go for specification, either it is power related or area related, how many inputs are there and how much power it will consume. Okay, and that IC can be used for communication purpose, that IC can be used for networking purpose. Different categories we can use. First you need to find out the specification of that IC. Okay, so for this you have you have design engineers in the top level. they will take the care of the specification. Okay, design engineers. Okay, so design engineers, they will do the specification. Okay, and next, architecture. Architecture is nothing but what? Architecture is nothing but they will do the outer shape. They will do the outer shape. That means, suppose if you want to design a CPU, okay, CPU means CPU consists of what? CPU internally consists of some what we call it consists of ALU, okay, it consists of ALU, okay, and memory unit, control unit, okay, and bus interface unit. All these are there, no? So that means here outline how we are designing this architecture, how we are planning. That is nothing but architectural level, okay. And the next, micro architecture. Micro architecture means in CPU you have a submodules, no? Submodules means you have ALU, micro so memory unit and control unit, bus interface unit. So all this you are designing, that is the architecture. So that is architecture. So you already studied about computer architecture. Computer architecture is nothing but what? How the computer will be there. Okay, inside what will be there. So that type of we call as a planning or doing the design is nothing but micro architecture or architecture. So you have architectural engineers. Okay, architectural engineers. Those are like around we call they will be like 25 to 30 years experience. They will take care of this architecture. Okay, they will take care of architecture. So basically, if you take the flow, so there is a hierarchy. Hierarchy means you have like SOC, and the next SOC system, module, and next you have gates, and next transistor. Okay, there is a top-down approach or bottom approach. So VLSI will follow top-down approach. So first system on chip. Again, system on chip consists of systems. That means in terms of microprocessor, microcontroller, or memory, and it consists of modules. Modules means what? Combination circuits, sequential circuits. Okay, and these are made with gates. Okay, these are made with AND gate, OR gate, NOT gate, and all those gates. And these are made with transistor. Transistor is nothing but MOSFET. Okay, so basically any system if they want to design, first they will do for top level module. So they will subdivide into different modules. This is nothing but hierarchy. Okay, so next you have RTL design. RTL design is nothing but register transfer level. Register transfer level. Okay, so register transfer level means, so like you have two types of languages, no? One is software language, and you have HDL. HDL is nothing but hardware descriptive language. So what is the difference between software language and hardware descriptive language? Means software language, they will develop only application. Suppose they will write for bank related operation, bank related, or airport related. Okay, they will make only application only. So suppose ATM related, ATM application. Okay, or a ticketing, railway ticketing system. They will make the application and give it to the employees, and based on that they will use that application. They will not make any hardware, but hardware descriptive language. So we can make the hardware by using a concept called synthesis. So synthesis is nothing but you are converting your descriptive language. Okay, you studied about digital, combinational, and sequential. So the descriptive language you are converting into gate level netlist. That is nothing but hardware. Okay, that is nothing but what? Hardware. Okay. So in this there are two types are there. Like you already studied, I think so. So one is VHDL. VHDL is nothing but a very high speed integrated circuits, very high speed integrated circuit, hardware descriptive language. Okay, and next one is Verilog HDL. Okay, Verilog HDL. So VHDL is it is a consist of a it is hard syntax, and it will follow olden language like Pascal, Ada, and Pascal. Okay, it is hard to learn. Okay, and this is used in the defense purpose. Okay, and defense, navy, and air force. Security is more for VHDL. Okay, and Verilog is it will follow C syntax. So basically, it was easy syntax and easy to learn, and so we can write easy program easily with a smaller level of lines. Okay, so again here you have like different like types of modeling styles are there, like switch level modeling, and next gate level modeling, and next data flow modeling, and behavioral modeling. So here RTL is nothing but we need to use switch level modeling means you are writing in terms of transistor CMOS circuit, that is switch level modeling. And gate level modeling means you are writing in terms of gates. Okay, those are gate level primitives are there, gate level modeling. And data flow modeling means you are writing in terms of expression. Suppose half adder is there, okay, or simple AND gate is there. What is the AND gate? Y equal to A and B, no? So you are writing in terms of expression. Behavior means I know the behavior of the circuit, half adder, what it will do. Okay, I will don't care about internal circuitry. So when I write the program in these two modules, that is nothing but RTL, register transfer level. How the data is transmitting through the registers inside. When you are converting your HDL into hardware descriptive language, that is in terms of flops. That will be in terms of flip flops. Okay, D flip flops. So how the data is transmitting to the different registers, that is nothing but RTL, register transfer level. So for this, for designing, you need RTL engineering. You need this RTL engineers. Okay, this is third one, RTL engineers. Okay, and this Verilog, when you are writing in a Verilog, this Verilog you can support. That means 90% we can support with designing, but up to FSM, suppose if you want to verify the circuit, we can write the Verilog code and test bench. Okay, so up to FSM we can write the test bench for this, and we can see the verification. Okay, but if you go for complex ICs like system on chip, or we are talking about IPs. IPs nothing but intellectual properties. So what are these IPs? These are nothing but RAM and I2C and some so UART. These are nothing but we call as IPs. Okay, intellectual properties. Okay, system on chip means all the processors and all those peripherals are there. That is nothing but system on chip. In the embedded, you call like Raspberry Pi. Raspberry Pi we call as a system on chip. Okay, so verifying these complex ICs, it's not possible with Verilog. Okay, you need to go for what system Verilog and UVM. System Verilog is nothing but it will support some like we call as a it will support two-state data type, and it is having OOPS concept, polymorphism, randomization, and randomization, constraint randomization, and you have child class, and like that some more advancements are there. Okay, so 90% we can verify the circuit by using system Verilog. Okay, this is also one HDL. This is also one HDL. Okay, and so here for the verification, if you use the system Verilog, so like that is robust type. So there is no particular type in SP. Suppose if you want to write for different I2C, okay, or like if you want to write for SPI, okay, separately you need to write. Okay, so that means what the companies has done, they came up with a standardized verification methodology, that is nothing but UVM. Okay, UVM is not a language. This is nothing but we call as a methodology. Methodology. You are using system Verilog in the UVM. Okay, universal verification methodologies. Okay, so for this you need DV engineers or ASIC verification engineers. We call as ASIC verification engineers. Okay, ASIC verification or DV engineers. Okay, so this is fourth engineers. Okay, so rigorously you need to verify. Okay, after designing rigorously you need to verify in the each and every corner cases, all those cases, corner cases, we need to give some assertions and all those things we need to use, and we need to do the verification. Okay, and if design is met, it will go to the next step. If design is not met, it will go to the RTL design. Okay, and here you see, so there is a logic synthesis. Okay, I told you, no, So that means here you will get gate level netlist. Hardware, you will get gate level netlist. Okay. But this is not non-optimized. This is what non-optimized. Okay. To make this as optimized, the synthesis engineers are there. Synthesis engineers. Okay. Here also you have some formal verification is there. Design verification means you need to use the languages like System Verilog and UVM to verify the circuit. Formal verification means you have FE engineers. They will use some mathematical formulas. They will use some mathematical formulas to verify your design. Okay, those we call as formal verification engineers. Okay, and next, synthesis is nothing but the synthesis engineers. They will do the synthesis. They will do for the constraints. Those are nothing but ATP. ATP is nothing but area, time, and power. Okay, so these are the constraints. So that should be low. It will take low area and it should be very fast and it should consume less power. These are nothing but constraints. Okay, so for this we need a synthesis engineers, and after synthesis you will get optimized netlist. Optimized netlist. Okay, and next DFT. DFT is nothing but you need to go for some test cases. What are those test cases? Means scan test, built-in self-test. Okay, these they will test your design whether this specification is matching or not. The specification is matching or not. Okay, for this you need what we call DFT engineers. Okay, we need DFT engineers. Okay, and next logic equivalency check. Logic equivalency check means what? Like whether your specification is matching your logic equivalency or not. Okay, that is nothing but a logic equivalency check. Okay, that is logic equivalency check. And next you have like static timing analysis. So here, static timing analysis means in the RTL design or in the verification, you are verifying that circuit. In HTA, there are two types are there. So before layout, that is pre-layout HTA and post-layout HTA. Okay. So this HTA is nothing but you are dealing with timing parameters. Okay. Timing parameters means you have like setup time, hold time, and clock skew, and jitter. Okay, jitter. So whatever the time related like propagation delay. Okay, so suppose if you consider any gate, so normally in the digital what you will say, so that means A and B, you are getting T y equal to what AB at zero time units. Okay, zero nanoseconds or zero time units, but there will be some delay for this gate. Okay, within that how much delay the input is propagating to the output, that is nothing but propagation delay. Okay, so for this you need HTA engineers. HTA engineers. Okay, for this you need HTA engineers. Okay, and next, so if design is met, it will go to the next step. If design is not met, it will go to the logic synthesis. Okay, and next you have PD flow, physical design. Okay, so till synthesis, this is front end, VLSI front end. Till synthesis, VLSI front end. Okay, front end. Okay, and from here, from HTA it will be back end. Okay, so PD means in the PD, physical design. Okay, so physical design you have partitioning, floor planning, power planning, placement, clock tree synthesis, routing, time enclosure. So that means like I will tell you with one example. Suppose here this PD people, what they will do, they will take the input from this front end design, and suppose if you want to build any building. Okay, what you will do, first you will make some planning, know how the building look like, where the bedroom should come. So that is nothing but you need to do some partitioning and floor planning. Okay, and also you need to do some power planning, and you need to do some placing, how the macro should be placed. Okay, how the macro should be placed, and clock tree synthesis. So different modules will not operate at different frequency, so there should be distribution of clock that will be done in clock tree. Routing is nothing but just connections. Okay, you need to do some connections. Okay, and timing closures and sign offs you need to do for physical design. This is totally back end. Okay, that will be done in the back end. So for this you need ST engineers, okay, synthesis, and you need ST engineers. No, so here you need ST engineers. Okay, so this is seventh, and you need PD engineers, physical design engineers. Okay, PD engineers. Parasitic extractions is nothing but what? So that means when you are fabricating any IC, so inside there will be copper interconnects. Okay, that copper interconnect consists of resistance and capacitance. Okay, so that extraction you are dealing with, that extraction, that is nothing but parasitic extraction. Okay, and after that you need to do post layout extraction, and after that you need to do the verification. Here also you need to do physical verification. Okay, some EM checks and all those things you need to do, and after that it will produce GDS2 file. The GDS2 file is given to fabrication. That fabrication will be done. mm, so here also you require PV engineers, PV engineer, post physical verification engineer, and it is given to fabrication. In the fabrication, you will do some N-weld technique or twin tube technique. So by using that, you can fabricate the your IC. Okay. So these many steps. Total you have in ASIC flow, you have 10 to 15 VLS engineers are required. So I'm not taught it about this fabrication engineers also. So total 10 to 15 VLS engineers are required in the ASIC design flow. Okay. So why we require this many stages? Means one person will not do, no, one company will not do. Okay, different levels, different specialized engineers are required. Okay, so why we need means suppose any IC is coming into the market, so that means that can be used for real-time application. That can be suppose if you are using for airplane, okay, aircraft you are using. Okay, so any malfunctioning in that IC, it may damage to property or it may damage to lives also. Okay, so that means before go releasing into market, rigorously we need to test, rigorously we need to verify, rigorously we need to do all those things. Okay, so so many, after so many tests, I think it will take around 6 months to 1 year to get into this IC. Okay, so this is the total ASIC design flow. I think hope you understood. Next, I am going with next topic. See here, yeah. So this is ASIC design flow. Okay. So basically, I told you know in the physical design. So if it is a PD course means you need to study about this floor planning. How the die size will be there. Okay, planning your floor. Floor planning is nothing but planning your floor. Okay, how the, so where you need to keep the RAMs, where you need to keep your CPU and all those things. How the, so you need to estimate the die size. Okay, die is nothing but it's like a, what we call, it's like a ICR, it's like a puppet. Okay, IO or macro placements, goal. So what are the goals? All macros should be placed in grid, no macro overlapping, and all those things you will design, will study in the floor planning. Okay, these are the inputs for the PD. So you are getting the input from the front end. I told you, no, synthesis. What is synthesis? You are converting your code into gate level netlist. Gate level netlist is nothing but .v file. Okay. And constraints. I told you what are the constraints? ATP. So you are doing synthesis, no? Synthesis, area, time, and power. So this after doing synthesis, you will get HDC file. Okay. Dot HDC file. That is also input for PD, and dot library file, and dot physical library. This is LEF file. And for multi-voltage domain design, that is UDF file. So these all inputs will be taken by PD, and they will do the design, physical design. Okay, and this is floor planning full chip. Okay, you need to estimate the die size and how the input and output devices are, output IO lines are there, and how the macros are placing. Okay, all those things you need to study about floor planning. Okay, IO planning means you will study about IO related things. Okay, like IO assignment file, specification of each port saying where should be placed. Okay, that is IO related planning. Floor planning means basically you have die area and standard cells. Standard cells are nothing but these are available in terms of logic gates, NAND gate, NOR gate, or adders and D flip flops. Okay, these are available in terms of standard cells. That standard cells you will take and you can place in the floor plan and place in the near die area. Okay, like that. And placement means where how I can place this IO plans and how I can place this exact standard cells. Okay, where the core area is there and like that. So these are the placements. What are the goals? Means cell utilization, jump, no congestion, no overlaps, good timing values. All those things you will study in the placements. Okay. And clock tree means I told you, different blocks are there. So different blocks will not operate at same clock frequency. So you need to divide the clock frequency and there will be a master clock. There will be a master clock. Master clock will divide into sub modules. Okay, that is nothing but clock tree synthesis. Routing is nothing but you will study about the connections. Okay, this involves creating global tracker routes. Okay, how the connections are made between the signal pins and metal layers. There will be different metal layers in the IC. Okay, the different metal layers with small distance. Okay, so that metal by metal layer, how the connections are made. Okay, and how the logical connectivity and physical connectivity are there, and router tries to fix DRC, design rule checks. Okay, that will study in the routing. And sign off checks means you need to check for electrical check, physical verification, and crosstalk. Crosstalk means some crosstalk unwanted signals are there. Okay, so different modules you are placing in that, there will be no interference between two modules. That is nothing but crosstalk. So you need to do for power estimation, IR drop analysis, power EM, signal AM, and layout versus schematics, design versus schema, DRC checks, antenna checks, all those things you will see in the sign off. Okay, so this is about basic PD, physical design. And coming to the design verification, this is front end. PD is the back end. Okay, physical design is the back end. So this is nothing but front end. Everywhere you see there is a VLSI is there. Okay, suppose your laptops, smartphones, your household applications. Are in automobiles also, anti-brake, anti-lock braking system, engine control system, um, brake control system, all those things. See, everywhere VLSI is there. Okay, and so you already studied about this microcontroller. Microcontroller is nothing but we are using only for particular application. That is microcontroller. I think you already studied about 8051 and microprocessor and SOC, system on chip, and FPGA. Okay. Uh, Microcontroller is nothing but only used for specific application. So all the peripherals are available within an own single IC. That is nothing but microcontroller. So we have consist of CPU, RAM, ROM, I2C, SPI, and UART. All those are available in a single IC. Okay. And what is the frequency? Frequency can be ranged from 1 megahertz to 300 megahertz. Okay. Microprocessor is nothing but you already studied about basic 8086 microprocessor. Okay, it consists of 60 bit of data lines and 20 bit of address lines, and whatever the it consists of ALU and register array and control unit. Okay, basic core i7 processor, which is there in your laptop or which is there in your desktop. That is nothing but microprocessor. So clock rate will be more in terms of gigahertz and 1 gigahertz to 4 gigahertz. Okay, and next system on chip. System on chip is nothing but we can call as it compresses all systems required components one into one piece of silicon. So suppose, so that is in one piece of silicon. So see here. So if you see, ARM processor is there, JTAG scan is there, voltage regulator, SRAM, flash, okay, and PLL, oscillator, RC, and Ethernet MAC, USART, SVI, two-wire interface, ADC, CAN, USB device, PWM, and synchronous timer counter. All these are available in a single IC. Okay, we call as system on chip. Okay, so basically how it is connected means there are some AMBA protocols are there, advanced microcontroller architecture. Okay, bus architecture, advanced microcontroller bus architecture. So you have like AXI, AHB, okay, HAB, APB, okay. By these buses, this will be communicated. See here, AHB, APB, okay. So like this, these are propagated, okay. So what are the components contents in the SOCR? Data processing units, embedded memory, and graphic processing unit, use ASB interface, video and audio processing. So all these are they were available in the SOC system on chip. Okay. So data processing means like you have DSP process and embedded memory, and this ARM processor. This is embedded processor. Okay. All those things are available in the in your SOC. Okay. FPGA is nothing but I told you, no, starting I told you what are the target devices, ASIC and FPGA. So FPGA is nothing but field programmable gate array. So it consists of what CLBs. These are nothing but configurable logic blocks. Okay. So configurable logic blocks means here these are IO blocks. All sides IO blocks are there. So with this IO blocks, I can connect input and output. In this like a CLB is the heart of the FPGA. Suppose CLB consists of what we call lookup table. It consists of lookup table and one T flip flop and one mux will be there. Okay. Suppose if you want to design any AND gate, you can write the Verilog code and you can convert, you can make the bitstream. Okay, you can port into the FPGA. That FPGA will be acting as the AND gate. Okay, we can reprogram. So this is mainly used for R&D purpose. Okay, for R&D purpose. Okay, suppose like we can use in the cell towers also. So previously we are using like 3G, 4G. Now we are using 5G. So in future you will get 6G also. Okay, future you will get new technology. So in the cell towers, what happens every time you will not replace this equipment as and you will not purchase. No, this is very costly. Okay, so here what you are doing if you are using FPGA. So depending on my technology, I can reprogram. Understood? I can reprogram that and I can use that FPGA. And in defense also, in defense different weapons are there. Okay, they are once they are purchasing. Okay, they are purchasing once. Suppose technology is changing means again they can't purchase. No, it will be very costly. So if you are using FPGA in that weapons or any drone related things, so based on the technology changes, they can reprogram that FPGA. Okay, based on the technology they can reprogram. So mainly FPGAs are used in defense and telecommunication, and so whatever the high security, and so if you are using FPGA means you need to use VHDL program. Okay, so this is FPGA, and this design flow I already explained. So I told you, no. So what are the VLSI target devices? FPGA and ASIC. FPGA and ASIC. These are the target devices. Okay. FPGA flow, if you see, so basically, what tool you are using means Xilinx Vivado you are using. Okay, basically, previously Xilinx is one company, but AMD acquired the Xilinx. Okay, now AMD acquired. Now we are using the Xilinx Vivado, that is from AMD. Okay, first what you need to write, first what you need to do, you need to write the program in HDL. Okay, so HDL, so hardware descriptive language. Okay, hardware descriptive language is nothing but you already studied digital electronics, that is combinational circuits, sequential circuits. Okay, so like how you are describing your circuit or a design in a textual format is nothing but hardware descriptive language. Okay, in textual format, in programming, that is nothing but HDL. Okay, so in this you are using Verilog and VHDL. Okay, so this Vivado tool. Okay, so Vivado tool, I told you synthesis, no. What is synthesis? You are converting your HDL into hardware. What is the hardware? Gate level netlist. That is nothing but schematic. Okay. So this Vivado tool will convert your HDL code into schematic. Okay. And there is a implementation will be done. What is implementation? So that is nothing but HDL source synthesis. Okay. Synthesis nothing but it will convert into gate level netlist. Gate level netlist is nothing but your circuit is in terms of gates, NAND gate, AND gate, OR gate, all those things. Okay. Implementation means you need to convert into, you need to translate, map, place, route. All those things will be done in the implementation. Okay. So like floor planning, routing, placement, and mapping will be done in the implementation. After implementation, it will generate the bit file, bit stream. Okay. You know that whatever the electronic ICs or whatever the electronic processors or FPGAs, that will understand only binary language. That is 0 and 1. Okay. In a microcontroller or microprocessor lab also, there you generated the hex file, no? Hex file that you are loading into microprocessor or microcontroller based on your application. Suppose if you are writing for LCD display, so based on your application will run. Okay, same like that. You are generating the bit stream. That bit stream you are loading into this FPGA. That FPGA will work. This is nothing but basic FPGA file. Okay. Bit file generation and hardware manager. That means you are loading into, there is some JTAG cable. Through the JTAG cable, you will connect your PC or laptop with this FPGA, and you load this your program into FPGA. Okay. So this is FPGA flow. So basically, design closures are one is functional closure. Functional closure means what? Through simulation, you can achieve this functional closure. Suppose if you are writing for half adder, so half adder, you know the truth table. That means you know sum and carry 0 0 0 1 1 0 1 1, sum 0 carry 0, sum 0, sum 1 carry 0, sum 1 carry 0, sum 0 carry 1. You know this. Okay. But how you are verifying means through waveforms. Through simulation you are seeing whether your design is correct or not. Okay. Power closure, proper timing closure will enhance the power efficiency. Okay. And timing closure means you need to do static timing analysis. That is I told you, no, timing related things like setup time, hold time, and a clock tree like clock skew, jitter, and all those things, timing related, propagation delay. So all this will you learn in the static timing analysis. Clock domain crossing means suppose in the digital you studied only with one clock only. Okay, one clock only you studied. So this CDC is nothing but when you are studying with different clocks. Okay, that is nothing but CDC. Okay, RDC is nothing but reset is also one of the important thing in the front end. Okay, reset domain crossing. Okay, there are like asynchronous reset and synchronous reset. Asynchronous active low reset, active high reset, synchronous active low reset, and active high reset. Okay, so in the industry, what we are using, why we are using, what is the reason for using that reset. Okay, that all those things you will study in the reset domain crossing. Okay. Basically, if you go for a front end, you can go for RTL design or you can go for ASIC SOC verification. Suppose if it is RTL design, we'll teach you digital electronics, Verilog projects, and STA, CDC, and RDC, and linting. Okay. And if you are going for ASIC verification, we'll teach digital electronics, Verilog. Okay. Verilog project will give. After that, we'll teach you system Verilog assertions, and UVM will teach you. Okay, we'll teach you this. Okay. So I told you, know what is the difference between Verilog and VHDL. In the starting, I told you. Okay, VHDL is nothing but very high speed integrated circuit hardware descriptive language. Okay, so if you see the Verilog, this is high level HDL, easy syntax, easy to learn, and multi level abstraction. So it will support C syntax. If you are comfortable with C, easily you can learn the Verilog. Okay. So one example I will tell you. Suppose AND gate is there. What are the input for AND gate? A and B, and output is what? Output equal to A and B. Okay. So I am writing with the module. So Verilog will start with module and it will end with end module. Okay. Module and end with end module. And my module name. What is my module name? This is we can call as identifier. What is my module name? And underscore gate. I need to declare the inputs and outputs. Input A comma B, output Y, and I'm using the continuous assignment statement. So this is data flow module. Data flow modeling I'm using. So Y equal to what? A and B. Y equal to A and B. So within how many lines my code is completed? 3 lines my code is completed. Same if you are going for VHDL, first you need to write with library IEEE, use IEEE STD logic underscore 1164 all. These are nothing but including your header files. And in the entity, you need to declare the inputs and outputs. Entity and underscore gate is port A in STD logic, B in STD logic, Y out STD logic. In the architecture, you need to write the logic. Architecture of gate is begin Y equal to A and B and end architecture. So that means around 12 lines of code. Here you have 3 lines of code, and here you have 12 lines of code. So which is easy? Verilog is easy. So Verilog is global. Wherever you see, so in a corporate for the ASIC, okay, we use Verilog only. Okay, wherever you go, you are using Verilog as a HCL language. Mainly in the defense and all those defense purpose. Okay, in the defense they use this VHDL. Okay, where you want high security. Okay, so these came into market around 2001. Okay, there is an IEEE that IEEE will standardize this. Okay, that is around 2001, and this is old language only. This is around 1999 you got this. Okay, so this is the difference between VHDL and Verilog. And analog layout means you are studying about floor planning, placement, matching, and design rule checks, routing, DRC and LVS, post layout simulation, and tape out. All those things you will study. So this you are studying about this analog layout. Analog layout also backend only. Like for the CMOS circuits, you are making the layouts. Layouts are nothing but just designing your stick diagrams. It's like a stick diagrams only. Okay. I think you studied about the stick diagrams. That you are studying about that analog layout. And next, these are the routing, DRC, all those things you will study. Okay. Common DRC rails. Okay. Common issues, analog layout concept. Okay. AMS is nothing but both analog and mixed signal design. AMS is nothing but what? Both analog and digital. Okay, that we call as analog and mixed signal. Okay, you'll study about both analog and digital. Okay, so this is a customized layout. Okay, like that. Okay, so you will study about schematic first simulation and yes, placement, routing, DRC, LVS, parasitic extraction, post layout, netlist simulation. So all those things analog related, you should be strong in the analog design. Okay, analog electronics. Okay, when you study about EMS. Okay, this is fully developed analog RF layout. Okay, ASIC chip design flow I told you specification. So coming to our Gnanodaya VLSI technologies, this is a premier institute for advanced VLSI studies. Okay, located in two places. One is located in Bangalore, that is Martali. Okay, Bangalore, Martali, and another is there in Hyderabad, near there in Hesar Nagar. SR Nagar metro station. It is near SR Nagar metro station. So, who are the faculty? Those are trained with 15 plus years of industry in the semiconductor domain, and they are proven track record in the placement and scholarship facilities. Okay, and unique features of Gnanodaya are 100% placement assistance will give. Okay, and industry standard course curriculum is there, and whatever the tools are there, so that 24 by 7 VPN support is given. Okay, and low cost for value for money. So VLSI, if you see wherever you see, you have VLSI like healthcare, automotive industry, telecommunication, consumer electronics. So wherever you see, you have VLSI. Okay, so coming to our placement process, first any requirement is coming. So we'll take from the client. Okay, we take from the client, and we will assist the student preparation resume as per the requirement. Okay, and we'll send the resume to the respective client. So after shortlisting, we will make the student to attend the interview. After that, final announcement. Okay. So before that, during that, there are so many like mock interviews will be there, weekend assessments will be there, assignments will be there, and we'll plan the technical seminars of the students to improve their communication skills. So after completing one module, either it may be digital or analog or basic module or tool related module. So what we'll do, we'll make one in a technical seminar, okay, and based on that we'll assess the marks, okay. Aptitude also, we'll give one topic. In the aptitude also, they make them to give one technical when aptitude seminar on this whatever the related aptitude. Why? Because in the written test for the aptitude you have 15 marks. Okay, so aptitude also will give some these type of activities will be there during your training. And so so gateway for semiconductor industry, Gnanodaya VLSI, and this already I told you. So what is eligibility means it should be minimum BE BTech in EC and triple E. Okay, EC and triple E means minimum in EC and triple E you are studying digital electronics and analog electronics, no? So that knowledge you need to have. Why? Because again we are brush upping the knowledge, but that knowledge you need to have, and you can be MTech or in VLSI or electronics. Minimum 60% score will be there, and good communication skills. Okay, and so training process, registration, discussing the fee and course, training period, preparation with mentor support, conducting mock interviews, 100% placement assistance. Okay, and these are the top companies for the placement support. Okay, Intel, Samsung, MediaTek, Qualcomm, Micron. Okay, some media companies like Synopsys, Insemi, Siant, uh, startups like Tasalvo, Mirafra, okay, and service-based companies like HCL, TCS, okay. These are our top companies, hiring companies. So these are the students got placed in from the Gnanodaya. So one is Amar Gopal. He placed in Apex in design verification. Ram Babu placed in Capgemini. Sham placed in L&T. These are our success. They got success after taking the course in the Gnanodaya VLSA. They got the knowledge from the experienced trainers, and they got the skills in the front end related and back end related physical design, and they got succeeded in the VLSI industry. Okay, and training, if you see, so there are we have three types of modules are there: physical design, analog layout, ASIC verification. Physical design is 6 months of course, and remaining are 4 months of course. Daily, like 1 hour class and lab practice will be there, and a weekend batch 6 hours per week will be there. Lab practice will be there. So intake is will take 15 to 20 students, and VPN support will be given, and 15 plus years of experience in Gnanodaya. So trainers are industry experience with 15 plus years of experience. 100% placement assistance will be given. Okay. So we can't give assurance. Just we'll give we can give the resume building, and whatever the activities are there for getting into the industry will make, and till you got placed we'll give the assistance. Okay, we'll send you after completing the your course, or about to complete, we will send based on the client requirement. We'll take the requirement one from the client, and we'll send your resumes to the client. Okay, resume building also there. Okay, okay, like that. This is training, and so any questions? So this is our contact information. Okay. So you can contact this number, or you can email. This is our website. Okay. And we have our app also, Gnanodaya VLS app also. There also you can make you can enroll your course, or you can access any course related things. Okay. Yes. Any doubts or any queries? Once again.